Okay, so we've been spending a lot of time in this chapter analyzing the relationship between different types of angles and circles. And we just barely touched on different types of segments and circles last class with theorem 10.14, I believe it was. And let me see if I can find it really quickly. Yeah, theorem 10.14. And really theorem 10.13 too. Both of these theorems have a lot to do with segments and how they relate to circles. Even 10.12, tangents, chords, secants, and the different types of relationships that happen within a circle when those different types of segments intersect. But now we're going to be talking about giving you a few more rules as it pertains to segments and circles. So we're going to start with right here with theorem 10.15. 10.15 says this: if two chords intersect in the interior of a circle, comma, we're going to stop right there and we're going to draw this. Two chords intersecting in the interior of a circle. What is a chord? If you remember, a chord is a segment whose endpoints are on the circle. So there's one chord, that's a segment, endpoints on the circle. And there's another chord. Okay? Here's what this says. Then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Here's what this is saying. Let's say each of these chords are now split into two parts. This chord right here has this section and this section. That's what it's referring to when it talks about the lengths of the segments of one chord. Here is the length of one segment of this chord and the length of the other segment of this chord. So when it's talking about the product, how the products of the lengths of the segments of both of the chords are equal, what it means is, let's call this length right here, we're going to call that little a, and we're going to call this little b. We'll call this little c and little d. What this theorem says is that a times b equals c times d. Okay? A times b equals c times d. So when we are solving for lengths of chords and segments, this is actually a very useful tool. Here's what I mean. Let's talk about this one. It's asking us for the length of EC. Okay, the length of EC is this length right here. We have two chords intersecting in the interior of a circle, and it wants us to find this length. We don't know this length, so when we don't know a length of any segment, we can call it x. And I'm going to use theorem 10.15 to set up an equation that I can solve. Well, since this is two chords intersecting in the interior of a circle, then we know that this length times this length will equal this length times this length. So I can set up an equation and solve. This length is 3 times x, because that's this length, equals 4 times 6. 3 times x just becomes 3x. 4 times 6 is 24. This 3 and this x are connected by multiplication, so I need to divide to get it away. Divide both sides by 3, and I get that x, which if you remember is EC, is 8. Okay? So EC, which we described as x, excuse me, is 8. All right, and we use theorem 10.15 to find that. All right, moving on to theorem 10.16. This one is one of those theorems that has a lot of confusing language, but really isn't that complicated. We just kind of need to sift through it a little bit. This one says, if two secant segments share the same endpoint outside of a circle. Okay, let's pause, stop, and draw that. Two secant segments. So remember, a secant segment is a line that goes through a circle. So we're going to draw a secant segment that has one endpoint on the circle and then has another endpoint outside the circle where both of these secants meet. Okay, so we'll draw it like this. Okay, here are our two secants. They both go through the circle. Okay, you could imagine that this continues on, but I'm not going to necessarily draw that, but you could imagine. so that the picture is a little clearer. And we're going to label each of these points, okay? So we're going to call this one A, this point A, that's that point right there. We're going to call this point B. We're going to call this point right here C. This is going to be D, and this will be E. That point is E, and that point is D, where they intersect. Okay, so there's our two secants intersect with an endpoint outside a circle. Then the product of the length of one secant segment, okay, so when it says the length of one secant segment, it means this length right here, all the way from this point to this point. That is a secant segment. That's the entire secant segment. So the product of the length of one secant segment, so that whole thing, so that's one part of it, and the length of its external segment, okay, so we still are dealing with the same secant, that's the secant segment. The external segment is this segment right there. That's the external, I'm just going to write EXT, external segment. Okay, so the product, that means we're multiplying, of the length of the secant segment and the length of the external segment equals the product of the length of the other secant and the length of its external segment. Okay, so we have two secants, and what this is saying is, we're going to write this out, that the secant segment, which is AB, times that same secant's external segment, so for the secant AB, its external segment is DB, so AB times DB is going to be equal to the length of this secant segment, which is CB, that's that whole secant segment, times the length of its external segment, which is EB. Okay, so this is how we can use secants to solve for different lengths when they intersect outside of a circle. Okay, so let's practice this right here. Here we have two secants intersecting outside of a circle, and it's asking us for the length of EC. We don't know the length of EC, so we're going to call it, we're going to use, what do we do when we don't know the length of some segment that we're looking for? We call it X. And then now we need to use theorem 10.16 to solve for this. So if you remember, we need to take the length of the whole segment and multiply it by its external segment. Let's just start with AB. So the length of the entire, what is the length of the entire secant segment from A to B? That's going to be 3 plus 6. So AB is 9. So if we're going to do AB times DB, which is what we wrote in this theorem, equals CB times EB, well, AB is 9, DB is 6, CB, we don't know exactly what CB is because we don't know what X is, but we do know that we can write it like this. We can write it as 4 plus X. The length of CB will be the same as 4 plus whatever this length is, X. And then we need to multiply that times EB, which is 4. Okay, and then we just need to solve this for X, and that will give us EC. 9 times 6 is 54. And I need to distribute this 4 in. 4 times 4 is 16. 4 times X is 4X. Subtract 16 from both sides to get the X term by itself. 54 minus 10 is 44, minus 6 is 38, I believe. Let me double check that. See, even math teachers need to double check their simple math sometimes. 54 minus 16 is 38. Yep, okay, good, I was right. So that's 38, and that equals 4x. And then since this 4 and this x are connected by multiplication, I need to divide both sides by 4. Okay, and when I divide 38 by 4, I get 9.5. So x equals 9.5. And that is how we use theorem 10.16 to solve for different segments. Okay, so Let me double check my math really quickly just to make sure that this is right. Yeah, I think that's right. Okay. So now we're going to introduce one more theorem really quickly. If a secant segment and a tangent segment share an endpoint outside a circle, comma, stop. Let's draw that. I'm going to try and draw a tangent right here. Tangent segment. And a secant share an endpoint outside a circle. So there's the endpoint that they share outside the circle. Then the product of the length of the secant segment and the length of its external segment. So that's the same thing that we have in the last theorem. Here's the whole secant segment. So let's enumerate this. I'm going to call this point A, this point B, this point C, and this point, I'll call it E. So the product of the length of the secant segment, which is CB in this case because that's the secant, and its external segment, which is EB, so CB times EB, will equal the square of the length of the tangent segment. Okay? The square of the length of the tangent segment, our tangent segment is this length AB, the length from the point of tangency to this endpoint. So CB times EB will equal the square of the length of that tangent segment. The tangent segment is AB, so the tangent segment squared will just be AB squared. Okay? So that's theorem 10.17. Let's practice using this theorem now. So here we have a secant segment and a tangent segment, and it's asking us to find the length of CB, which is our tangent segment. We don't know CB, so we're going to use a variable in its place. And what we know is that the length of the secant segment, which is AB, times its external segment, which is DB, will equal the length of the tangent segment, which is CB squared, or BC. I could write it as BC as well. And now I just need to plug in the values for this. AB is 3 plus 6, which is 9. DB is 6. And that will equal what we have called x squared. 9 times 6 is 54. That equals x squared. And now to get x by itself, I need to take the square root of both sides and then simplify this radical to get x. Square root of x squared is just x. Square root of 54, we've already seen that it's 9 times 6, so that's the same as the square root of 9 times 6. And I wrote it this way because 9 is a perfect square, so that can come outside of the radical. I can't do anything with this 6, so it just stays there. So x is 3 root 6, which is BC. So BC is 3 root 6. Okay. What we're going to do now is I have 4 practice problems that I want you to try. We're going to do the first one together, and then I want you to do the other 3. And there's also this slide in here that is a good barometer, a good example of something that might be good to go on your cheat sheet. And in fact, I would add what the rules are under here. So for example, if 2 chords are intersecting inside the circle, I would write what that rule is as it applies to this picture underneath here, and you can add that whole thing to your cheat sheet. So 4 practice problems. We have these 2 here, and we have these 2 here. They say honors. They are honors level problems. I want everyone to do them. I want you to do those, and when you're done, check them all with me. Let's do this first one together. So the first thing that you need to do when you're doing these types of problems is to recognize what types of segments are interacting with the circle. In this case, these are 2 secants. Okay, so 2 secants, what's our theorem that refers to 2 secants? Well, that's theorem 10.16. So we're going to be dealing with our secant segments and our external segments, etc. So what theorem 10.16 says, if you remember, is that the product of the secant segment and its external segment will equal the product of the other secant segment times its external segment. Okay, so in our case, this whole secant segment, AB, is 10 plus x. I'm always going to write that in parentheses because we're going to be multiplying it by something. We're going to be multiplying it by DB, which is the external segment, which is just 10. okay? And that will equal this secant segment, which is CB, which is 11 plus 9, so 20, times its external segment, which is 9. And now I just need to solve this equation for x. I need to distribute this 10 in. 10 times 10 is 100. 10 times x is 10x. 20 times 9, if you do that in your calculator, you get that it is 180. And now I just need to simplify. I'm going to subtract. I need to get this term by itself on a side since these aren't like terms. So I'm going to subtract 100 from both sides. And I get that 10x is 80. And then this is connected to this x by multiplication, so I need to divide. When I divide both sides by 10, I get that x is 8. Okay, so there's another example of how to use theorem 10.16. This one is using theorem 10.17. So if you need some help, you can do that. Do these two. Finish this one. Do this problem. Give your best try at both of these. Check them with me when you're done, and then when you're done, you can move on to your practice problems. Thanks, guys.